is Hugo Mora. I'm your team with Diego and Gustavo, and I did the problem number 1, that is considering the signal ht, obtain h omega analytically, and also obtain h omega, but using the definite interval. And for last one, use MATLAB or Wolfram to obtain h omega and compare my results with the step A. So there's the steps that I did. So basically, this is the step A that was using depending, that is 2t plus 2 from -1 to 0, and then the 2 that is from 0 to 1. And first I derivative to obtain the function gt, to change the name, and this is what I obtain. This is -2 because this is the down from here, and then from this I got that gt is equal to mt minus 2 integral of t plus 1. That is the distance from here, that is 0, to here, that is 1. And then from this I obtain that first there's a step from 0 to 2, that is this one, and then from 2 to 0, that is this one, that is -2, 2, and then I obtain that mt is equal to 2 integral of t plus 1, that is this distance, and then minus 2 integral of t, that is this one. Then I obtain there is 2 exponential j omega minus 2, because this is exponential of 0, that is 1, and then I obtain 1 multiplied by 2, that is 2, and then for et it's mt minus 2 integral of t minus 1. For the reason g omega, it's 2 exponential j omega over omega j minus 2 over j omega minus 2 exponential minus j omega. The minus is because there is -1, that is t0, and this is multiplied by t0. Then my function h omega is the integration of all of this again, and it's basically 2 exponential j omega over j square omega square minus 2 j square omega square minus 2 exponential minus j omega over j omega. So transforming from the j, that is the imaginary number, you obtain this function, the graph, and I show you here. Then by the finite integral I use this, that 2t plus 2 is from -1 to 0, depending on t, that is the time, and then 2, that is from 0 to 1, and 0 is elsewhere. So there is the function that I'm going to use to obtain h omega. That was is the integral of 2t plus 2 multiplying this, that is exponential of minus j omega t plus this function, that is 2 for the exponential minus j omega t. Then I multiply this one them these two intervals, and then to solve this one, I use the integration by parts, and I obtain this equation. Let's see, that is 2t exponential minus j t omega minus j omega plus 2 minus j omega t over j omega, and the function is from, well, everywhere over here, that is from 0, well, from minus 1 to 0, and then from 0 to 1, this function, that is the second one. Then solving all this, I obtain that h omega is equal to 2 exponential j omega over square omega square, and then 2 plus 2 exponential minus j omega over j omega, and then I show you the graph that I obtained. This is the MATLAB that I use, and then I plot 3 different views that are of this. Yes, there's that I obtained using by hand, that is equal to using the Fourier transform, and then there is the original graph. And comparing my results, I noticed that it's correct because I obtained the same plot, because in any of the case this is the correct one, the Fourier transform, and then this is the to know if I am correct using the by hand and comparing to the Fourier transform.
So in this first part I am going to explain the exercise of exponential Fourier series and trigonometric Fourier series. First we go to this exponential Fourier series. Here we have our graph. You can divide it into parts. The first part is going to be -1 to 0, and the second part is going to be 0 to 1. The first part can be represented by this function, 2 by t plus 2 over the period, and the second part is going to be represented as this number. The total period is going to be 3 because we have to do the representation over -1 to 2. So here we have our period, and w0, that is going to be 2 pi divided by 3. Then we have our integral, 2 integrals. The first integral is going to be this function multiplied by this exponential function, and we have to put 1 over the period, and again here in the second integral we have to do the same, 1 divided by 3, and the function, there's going to be this number over this exponential function. Then we can divide this first integral in 2 parts. The first part is going to be 2 by t by the exponential function, and then we extract the 2 in order to get this constant. Then the result of this function over this period, -1 to 0, is going to be this result, this whole number. And then the second part of the first integral is going to be this. We extract the 2 in order to get this constant, and we have the result. Then the second integral is going to be almost the same as this function. The only thing that changes is going to be the period. Here the period is going to be -1 to 0, and then here is going to be 0 to 1. Here we have the result of this integral and the other integral. Then we have to obtain f0 using these integrals, 1 divided by the period, and integrating 2 by t plus 2, and then the second integral we have to only integrate 2. These two functions are the same as the other ones that we saw, and then we have the integrals and the results. We sum the three results and we get our f0, that is going to be 1. Then the only thing that we have to do now is to make the Fourier series representation. We put f0 plus the summatory over minus infinite to infinite, and well, this whole number is going to be the result of our integrals that we have already done, multiplied by this exponential number. So here we have our second exercise, the trigonometric Fourier series representation. We are going to use the two functions as the same as the past exercise, also the same period and the same W0. What we have to do here is get the an coefficient, integrating these two functions. The first function is going to be 2 divided by the period over minus 1 to 0, the function multiplied by cosine of n of W0 of t by t. Then the second integral is going to be 2 divided by the period over 0 to 1. The function is going to be this number multiplied by cosine of n by W0 by t. As the same as the past exercise, we can divide this first integral into parts. The first part is going to be this, and well, we have to do the integration and we get this result. Then the second part of this first integral is going to be this, and then we get the result of this integral over this period, 1 to 0. And then the second integral is going to be almost the same as this. The only thing that changes is going to be the period. Here is going to be minus 1 to 0, and here is going to be 0 to 1. We integrate and we get this result, and we sum these three results, this, and this, and we get an coefficient. Then we have to get Pn coefficient. It's going to be almost the same as the an coefficient. The only thing that changes is going to be this part. The function is going to be multiplied by sine of n of W0 by t, and the same here. We divide this first integral into parts. Here we integrate and we get this result. The second part is going to be this, and then the result is going to be this part. The second integral is going to be this, almost the same as this. The only thing that changes is the period. Here is minus 1 to 0, and here is 0 to 1. We have the result, and we sum these three results in order to get Pn, and here we have Pn coefficient. Then we have to get A0, that is going to be this formula, 1 divided by the period, integrating the first function over its period, minus 1 to 0, and the second function is going to be 2, but in the period 0 to 1, and also multiplied by 1 divided by the period. We do these two integrations and we get our result, or constant, that is going to be only 1. Then what we have to do is make the trigonometric Fourier representation. We put 1 plus the summatory of the an coefficient multiplied by cosine of n of w0 of t. Then we do the summatory. We put bn multiplied by sine of n by t by w0, and here we have. So now I'm going to explain the codes that I made for the two exercises. The first one is going to be the exponential Fourier series representation. There is this code. This code is almost the same as the one that I made on the activity. The only thing that I changed, well, one of the things that I changed is this part, that is the fn coefficient. And actually, and here is this is the f0 coefficient that multiplies this matrix. And well, then another thing that I changed is that if you see when n is equal to 0, it causes an indetermination, because you can't divide any number by 0 because it causes an indetermination. So I divided the for loop into parts in order to avoid that indetermination. So here I'm making the summatory for 1 to infinite, or the number of iterations, and then in this other part I'm making the summatory of minus infinite to 1, or minus iterations to 1, and then I just graph this thing, and well, this is how it looks, a graph with 10 iterations. Let's see, let's try with 100 iterations. It takes some time, but we're going to get the result soon. So here we have, you know, this approximates more to the graph that we got to make the exercise. Then we have the trigonometric Fourier series representation. Here I don't have to divide these 4 into parts because we don't have to use n0. We have to use only n1 to infinite, or in this case n1 to iterations. Here I have the an coefficient and bn coefficient, and w0 and a0. And let's see how it looks with 10 iterations. Here we have, let's try with 100 iterations. And well, that sound is almost the same as the original graph. So that's it.
Okay, so now for the explanation of the problem number 3. So this one is the function that we got from problem 2. And this is the form that it has, the first one. So as we remember, this kind of signal is periodic, which means that we don't quite need it. We only need like a fragment of this breadth, the analogy goes, to be able to obtain a function. So we separated this one into the an and the bn and multiplied by cosine of omega 0 t, well, n omega 0 t. So the fragment that we choose is from a1 through a3 and from b1 through b3, meaning that only the sums apply for n1 through n3 and the a0 as established before. So with the help of Wolfram, we made all these calculations to get the a n part of 1, the a n part of 2, and the a n part of 3, and same with b. And then we made them into this form with the a and c, this value, times the cosine of n to thirds of pi t. And that gave us this formula in the ft, in the time domain. So to convert it into the frequency domain for the fw, this is the form that we used. So x, meaning anything before the cosine as a coefficient, times the cosine of omega t, it's equal to the same x times a half of the delta of omega minus omega t plus the delta of omega plus omega 0. Sorry, omega 0. So this is for the cosine and this is for the sine. So the difference is the plus and minus sign in here, and the 1/2 and 1/2 imaginary, so to j in this case. Let's call it j. So by making all these calculations once again, for A1, A2, A3, B1, B2, B3, this is the form that we got for the f omega. And this is the formula, well, the function that it's gotten. So for the MATLAB plot, we took the ft, well, the fw, the fw part, instead of the cosine of with the deltas, we took it as the exponentials because it's easier to plug an exponential into MATLAB. So we got this exponential, and this 1/2 that is dividing passes to multiply the x, so that this becomes a common term between the sine and the cosine. So it is a common term with the only variation of the coefficient. So for that, we could factorize it, and we get the exponential of j omega 0 t minus the exponential of minus j omega 0 t times x over 2 minus the j y over 2. So we took this procedure, and these are the calculations that we helped Wolfram for the before part, and this is the code that we got. So in the code we inputted this whole part of the exponentials, and then this is the graph that we got without the offset. And for the second part, we got the offset like by moving it a little bit, only by adding to the function the period, another period, so that the off phase, well, the offset of the function is the period as a factor.